Good day. In the last part of Study Unit 7, we are going to look at these sections in Chapter 15, so you can turn to page 365, please. At the outcomes in the study guide, you should be able to understand why post hoc tests are necessary after the ANOVA analysis was done. You should also apply the post hoc test and draw conclusions from it. And lastly, test whether the assumptions for the ANOVA is met or not. When we conducted an ANOVA analysis, we stated in the null hypothesis that the population means were equal to each other. So, for instance, if we have 3 population means, then this will be our statement for our null hypothesis in the ANOVA. But if we rejected that null hypothesis, then it means that there will be differences between the different population means. So that's when we conduct post hoc tests to see which population means will statistically be different from one another. Now we will test all the different pairs for the population means simultaneously, and we can use this guideline to determine how many tests we need to conduct. So let's say, for instance, that we have 3 groups. Then our number of tests will be the number of groups times the number of groups minus 1 divided by 2. So 3 times 2 divided by 2 will give us 3 tests. Since we will test population mean 1 against population mean 2, population mean 1 against population mean 3, and population mean 2 against population mean 3. So these will be our post hoc test. In the null hypothesis, we state that our population means are equal, and in the alternative hypothesis that our population means are not equal. If you have 4 groups, for instance, then you will have 6 tests. Since 4 times 3 divided by 2 will be 12 divided by 2, so that will give you 6 tests. So you will test population mean 1 against 2, 1 against 3, 1 against 4, 2 against 3, 2 against 4, and 3 against 4, etc. The test that we are going to do is called Tukey's Honestly Significance Differences Test, or Tukey's HSD test for short. And the formula for the test statistic for this test is given by this formula. So if you look at the numerator first of all, we get the absolute difference between the 2 individual group means that we are testing. So if I want to test population mean 1 against population mean 2, I will take the group mean for group 1 minus the group mean for group 2. Or if I test population mean 2 against 4, for instance, then I will subtract the group mean for group 4 from the group mean of group 2, etc. Then in the denominator, we have the square root of the MSE divided by the number of items within each group. We will use the following steps in our post hoc test. In step 1, you state all the post hoc hypotheses for the different combination of population means that you are going to test. Then in step 2, you need to calculate the test statistic for each comparison. So we said in that test statistic, you will need the number of observations within each group, the individual group means for each group, and then your MSE. So you can obtain all these information from your computer output. And then in step 3, we are going to determine the Q-critical values so that we can estimate the p-values to make our conclusion for each post hoc test. So the Q-critical values we read off from the Q table, and it works similar to the F table. The Q table is given for a 5% and for a 1% significance level, and V1 also gives us the column number that we are going to use in our table, and the column number will be given by the number of groups. And then our row number is indicated by V2, and we obtain that by taking the total number of items in our ANOVA study minus the number of groups. And then we can use those Q critical values to estimate the p-values and compare it against our significance level. If our p-value is less than or equal to our significance level, we will reject the null hypothesis. But if our p-value is more than our significance level, then we do not reject the null hypothesis. Please take note that we only have a 5% and a 1% Q table, so we can only estimate the p-values with those tables. So we can say that the p-value is going to be less than 0.01, more than 0.05, or between 0.01 and 0.05. We can get the exact p-values from our computer output, and I'll show you later in the chapter how we can read that off. So then you make your conclusion for each comparison, whether you reject the null hypothesis or not. And then finally, in step 5, you will draw an overall conclusion for the entire test. So if you rejected the null hypothesis, you will state that those population means will differ from each other. And for the comparisons where you did not reject the null hypothesis, you will say that those population means will not differ from each other. We can estimate our p-values from the Q tables as follows. If our test statistic that you calculate is less than a Q critical value from the 0.05 Q table, it means that your p-value will be greater than 0.05. So the null hypothesis will not be rejected. But if your test statistic that you calculate falls between the two Q critical values from the two tables, then it means that your p-value will be between 0.01 and 0.05. So you can reject the null hypothesis at a 5% significance level, but not at a 1% significance level. Or if your test statistic is more than a Q critical value from the 0.01 Q table, it means that your p-value will be less than 0.01. So your null hypothesis can be rejected. Let's conduct a post-hoc test for example 15.1. Just to recap, we had 4 different groups for the 4 different teaching styles, and we had 5 observations within each group. So our total number of items across the 4 groups were 20. And we determined the group means for the 4 different groups in part 1. And then in part 1, I also showed you where to read off the MSE value from your ANOVA table. Since we are working with 4 groups, it means that we are going to have 6 post-hoc tests that we need to conduct. So in step 1, you state your 6 post-hoc hypotheses. Then in step 2, we need to calculate the test statistic for each of these post-hoc tests. Our MSE was 24.25, and we had 5 observations within each group. So the calculation below the line will stay the same each time. It's just the absolute difference of the group means that will change. So for instance, for group 1 and 2, I'm going to take 82.4 minus 74.2. If I calculate the test statistic for group 2 and 4, then I'm going to take 74.2 minus 55.6, etc. And I do that for all 6 test statistics. In step 3, we need to determine our Q critical values from the 2 Q tables. So our column number that we are going to use is 4, since our number of groups was 4, and our row number will be 20 minus 4, so that will be row 16. If you go to the 0.05 Q table, to column 4, row 16, you will see that your Q critical value will be 4.05. And if you go to column 4, row 16 in your 0.01 Q table, you will see that your Q critical value will be 5.19. Now, if we do the comparisons in step 4 to estimate our p-values, you will see that the test statistic you calculated for group 1 and 2 was 3.72, and that will be less than 4.05. So the value from the 0.05 Q table, so that means that our p-value will be greater than 0.05. So we do not reject the null hypothesis. If you look at the next comparison for group 1 and 3, that test statistic was 7.99, which is more than the value from the 0.01 Q table. So that means that our p-value will be less than 0.01, so we can reject the null hypothesis. And then if you compare group 1 and 4, that test statistic was 12.12, which will be greater than the Q critical value from the 0.01 table. So our p-value will be less than 0.01, so we can reject the null hypothesis. If you compare groups 2 and 3, our test statistic is 4.27. So that value will lie between the two Q critical values from the 0.01 and 0.05 Q tables. So it means that our p-value will be between 0.01 and 0.05. So we can reject the null hypothesis, but only at a 5% significance level, since p will be less than 0.05, but p will be more than 0.01, so we can't reject it at a 1% significance level. If we compare groups 2 and 4, our test statistic is 8.45, which is greater than the Q critical value from the 0.01 Q table. So our p-value is less than 0.01, so we can reject the null hypothesis. And then lastly, the test statistic for comparing groups 3 and 4 is 4.18, which again lies between the two Q critical values from our two Q tables. So our p-value will be between 0.01 and 0.05. So we can reject the null hypothesis at a 5% significance level, but not at a 1% significance level. Then, for step 5, we need to draw the overall conclusion. So if you rejected the null hypothesis for a comparison, then it means that those population means are not going to be equal to each other. But if you did not reject the null hypothesis, then those population means will be equal to each other. So the only population means that are equal is population mean 1 and 2, and all the other population means will be significantly different from one another. If a question asks you to conduct a post-hoc test using the relevant p-values, then you can use the exact p-values from the computer output. Then you don't need to estimate it from your Q tables. There's two group-wise comparisons test p-values on your computer output, so just make sure that you use Tukey's group-wise comparisons test table and not Scheffé's. Since the test statistic that we use in the post-hoc test are Tukey's test statistic. Now you can read off the p-values either in the column or the row. For instance, if I want to test population means 1 and 2, then I can read it off there, or I can read it off there. It's just a matrix. It gives me the same value. Or if I want to test groups 2 and 4, for instance, then I can read the value off there, or I can obtain the value here. If you conduct a post-hoc test with the exact p-values, you also state your post-hoc hypotheses for the different population means that you're going to test. But then instead of estimating the p-values, you can just write down the p-value for the two population means that you are testing. So in the first comparison, we want to test 1 and 2. So you write down the p-value, and that, let's say we test it at a 5% significance level, then that p-value will be greater than 0.05. So we do not reject the null hypothesis. If you test population means 1 and 3, your p-value is 0.0004 and that will be less than 0.05, so we reject the null hypothesis. If we test population means 1 and 4, then our p-value will be 0.0002. That will also be less than 0.05, so we can reject the null hypothesis, etc. We do it for all the comparisons. And then we still need to draw the overall conclusion. So you will come to the same conclusion as we did with the estimated values. You can try exercise 2.2 in your textbook, please. The computer output was distributed in class, or alternatively you can find it on Efundi. The last section in chapter 15 looks at the testing of the ANOVA assumptions. There's 3 ANOVA assumptions that you should take note of, and you should be able to check these assumptions whether they are met or not. Usually we will check the assumptions first before conducting any statistical test. Otherwise, if these assumptions are not met, then the conclusions that you draw from the hypothesis test might not be reliable. So first of all, we need to check whether our observations are independent. So that means that we conduct a random experiment. So it means that if we select our items or people from our population for our sample, we will do that randomly, and we will randomly assign the items or people to the different groups. And then for the other 2 assumptions, for normality and homogeneity of variances, we use the residual plots on the output to check them. To test if the data is normally distributed, we check the normal probability plot of the residuals. The residuals should lie more or less on a straight line, but if there are large deviations from a straight line, then that assumption will not be met. If you look at the normal probability plot of the residuals on the computer output of the chapter example, you can see that there's clear deviations from a straight line, so this assumption will not be met. In testing the homogeneity of variances assumption, we check the residuals versus factor level graph on the computer output. You should have a horizontal band appearance, so the variances should be roughly the same for the different groups in this graph, like in example A. But if there is a pattern where the variances fans out or funnels in, like for instance in graph B, then this assumption will not be met. But this is very subjective in nature, so a more objective way of testing this assumption is to look at Bartlett's chi-square test that results on the ANOVA output. If the p-value for this test is less than or equal to alpha, then your variances are not equal. But if your p-value is greater than alpha, then the variances are equal, because the null hypothesis for this test states that your variances are equal. If you look at the residuals versus factor levels graph for the textbook example, you can see that the variances are roughly the same in that graph, so this assumption will be met, and this is confirmed with the results of Bartlett's chi-square test, since the p-value is equal to 1, so it will be greater than alpha, irrespective if alpha is 1% or 5%. So you will not reject the null hypothesis, so the variances are equal. You can then try exercise 2.3 in your textbook on the assumptions, please, and then also the class exercise that was distributed in class.